My name is Nick Bucher, and I'm here to present my final project in robotics, mobile AR game development and robots. So for this project, I made an AR game using Unity, a game engine, Vuforia, which is an augmented reality package for Unity, ROS, the robot operating system, and Stage, which is a program for ROS that's used to test programs before you run them on robots. The goal of this game is to land a helicopter on a moving target, and two AR targets are used for positioning the player. One is used for the robot frame, which contains the in-game target, and one is used for the world frame, which contains the ground and the player. While the AR application is running, the ROS application is also running to move the robot. So also in this project, I'll be talking about graphics techniques that I use to simulate depth in the AR application. And this application is running on an Android phone. So as seen on the picture on the right, Stage is used to test robot movement, and the robot used for this project is the Pioneer 3DX robot. And the topic used is the geometry messages twist topic. Robot movement is kept fairly simple for this AR game, and that is because the AR targets will need to be detected, and so for that to happen, the robot needs to rotate fairly slowly. And to rotate the robot, the Catkin package that we tested using Stage publishes on that geometry messages twist topic. So as you can see in the picture, there's an AR target that is placed on the robot, as well as an AR target that's placed on the ground. And each target represents the robot and ground frame, respectively. So for testing the AR gameplay, I used Unity, which is seen in the picture on the right, and my laptop webcam could be used for testing the AR capabilities. Once the application was ready, an Android application, or APK file, was built in Unity and then transferred and installed to my Android device really throughout the entire testing process. So you could see on the right there, the helicopter hasn't been added yet, and that's sort of the development version of the game. So throughout the entire game, Raycasting is used for detecting intersection checks. And raycasting is a method of checking the intersection of a line in a scene with every other collider in the scene. And information about the first point of intersection is returned by the raycast function. This includes information about the object that was hit by this raycast. And collider checks, so object collider checks, can be reduced and selected through layer masks and physics layers, which are very useful in selecting different categories of objects that you want to intersect with. So physics layers are sort of the ID that you put on each collider in the scene, and layer masks are how you select and mask out those IDs. Box casting is also a term we'll be using, which is basically the same as raycasting, but uses a box, or rectangular prism, with certain properties which you can specify in the function call. And those properties could include the length and the width of the box, and the distance the box will be cast to. So using box casting, you can basically translate this box in the scene, this invisible box in the scene, and detect the first collider that is intersected with. So for implementing controls, first, when a pointer click is detected, a raycast is initiated that it starts at the pointer position in the scene and moves in the direction of the camera. So the first collider that is hit by this raycast from the pointer position is returned. And by using layer masks, I can reduce the number of colliders that are being checked, and by doing that, you can just mask it out basically just to the controls layers, which are those arrows you can see on the picture on the right. So for each one of those arrows has a box collider surrounding it, which is used in this check. And so whenever the pointer down event is hit or is registered, the player starts moving in that direction, and then when the pointer up event is registered, the player stops moving. So shadows are created in this project by raycasting downwards into the scene from both the player and the target object. And as in the same way, layer masks are used to restrict this collision. For the player, we're restricting the collision to both the target and the ground layers. However, for the target, we just want to be able to intersect with the ground layer. And the reason for that is if the raycast starts in the target collider, then the first collider it will return is the target collider unless a layer mask is specified. So once a intersection point is detected, a shadow object is moved to the position of intersection, and the sort of effect that you see in the picture on the right is displayed. And by doing this entire process, we can detect where the player is in relation to all the other objects in the scene a little bit better. And while the normal lights in Unity do cast shadows, this precise technique of showing exactly where the player is and exactly where the target is really does help with figuring out where they are, perceiving where they are in the scene. Now, a similar method is used for target and ground intersection for the player. So every time step, the player is translated downwards a certain amount, which is calculated by using a gravity force to figure out the acceleration and velocity of the player. Now, every time this is performed, several raycast checks are performed to detect whether the player has won by landing on the target or lost by landing on the ground. Now, if the player's movement raycast intersects with the target, then a windscreen is displayed. The target stops, so everything basically stops moving. The player stops moving, and the distance from the player to the center of the player hit position to the center of the target is calculated and displayed as a percentage on the screen. Also, in this process, the player is parented to the target to fix its position to the target, so that if the actual AR image targets are moved, the player is moved along with it, and it looks natural. Intersection with the ground collider does indicate failure, and then the lose screen is displayed. So here's a demo of the project in action. So future work after this project could include a cost-benefit analysis of different augmented reality packages, such as Google AR Core, Apple AR Kit, and Vuforia, to determine the best AR package that should be used in the future. And while I have an Android device, AR Core was impossible to use for this project since my particular phone was not supported by Google. Now, controlling a robot from a mobile device could be also useful research to perform. And this sort of thing could be used, for example, to move a robot with an AR image to a door, and it could maybe act like a key and unlock it. And like for this sort of research, Ross Bridge could be used to communicate between the AR application and the Ross application running on the robot. And this could be used for a variety of different applications, this sort of AR robot combination. So over the course of this project, a proof of concept augmented reality game that combines AR with robots was developed, and as you can see on the right, the game can be played through and either won or lost, with the accuracy being displayed on the final picture there. So this game contains a gameplay framework that can be built upon or used to test other AR tools, such as described earlier, like the Google's and Apple's AR tools. Thank you.